Can you see this?
Yes, it's working.
Excellent.
Right.
All right, awesome. Well, thank you. My name is Andre Thomas. I'm a professor in the visualization department and the director of the Life Lab. I'm going to share with you some new process we've developed in the Life Lab to help digital twins, although we don't actually call it digital twins ourselves, because there's a lot of, as you're going to see throughout the day, a lot of different definitions of what a digital twin is and how to use it, from medical application to just IoT and so on. And I don't know that there is one established definition that everybody agrees on. So what we've been focusing on is a simple problem that was posed to me several years ago by a very large engineering company. And I came and said, we have this aging infrastructure all over the US, all over the world, facilities that are, industrial. We don't really know the state of them. The plans aren't up to date. We don't necessarily have digital files of them. And so a lot of changes have been made to these facilities, and the workforce is aging. And so there's a middle layer of workforce that's missing and a young workforce coming in. Now, the older workforce that's about to retire, they obviously know their facilities in and out. They know every little dial, every gauge, and so on. They know what has changed, why it has changed, and so on. But a lot of that knowledge hasn't been captured anywhere. It's not available to anybody, especially as young workforce. And so the problem is, how do you, number one, know what you actually have in your facility? And then number two, how do you train a new incoming workforce and keep it also up to date? Because we all know we have great design tools that when we start a new plant, a new building, an airport, you name it, they really help us build it. But 6 months after a facility is built, things are going to have changed. And those original plans are rarely kept up to date, because it's usually another company that's now operating and managing the plant versus the architects or the designers that actually created it. So how do we deal with that? How do we capture the built environment? Well, currently, there are two methods. One is photogrammetry, and it's a method of taking hundreds or thousands of pictures of an object, like what you see here, and then the computer can digitally recreate that object. And what you see here is a statue, and you go around the statue, and as you can see from all these different angles, you create pictures, and then the computer can stitch it together and create a 3D mesh. Well, the same can be done with a whole street, right, of houses. And here you can see on the left-hand side, there's a textured view. In fact, that's what Google Earth uses, with very process. And then on the right, you see the resulting mesh, the 3D mesh that comes from it. And as you can probably see, if you look closer, it really leaves something to be desired in terms of accuracy. There's a lot of inaccurate things. And yes, when you put a texture on it, you kind of make out what it is, but we're really missing detail. And in order to capture that detail, you need many, many more photographs. And so now it becomes not necessarily feasible, too time consuming to actually do this. So another method that's been developed that many of you might be familiar with is LiDAR scanning. LiDAR scanning uses a laser scan that rotates 360 degrees, or now there's handheld scanners, and generates a point cloud. So lots of little points from the environment. Here's a little street scene that you can see. And here's an industrial environment. It's like, okay, well, now we can see much more detail, right? We see these little pebbles on the ground. We can make out switches on the machinery, and so on. So now we're getting to that detail. LiDAR scanning is millimeter accurate. However, you have to have lots of different scanning stations. I get to in a minute, but first, what LiDAR scans produce is a point cloud. Now, point cloud is what might appear solid right here is nothing but just a massive amount of points. And you can see it here in the top. So all of these points together and then generate this image. Now, points themselves are not structured data. They don't have any information other than a location information. They're not connected through any way. And so now cleanup has to happen to actually create out of the point cloud meshes, individual objects that are useful, that we can do something with. Now you could say, well, you know, if we have this facility here, we can easily attach data to any point. Sure, you could do that and give each point a unique number or identifier and attach data to it. But I think where we're headed with digital twins and applications, we want something more than just points. The other issue with LiDAR scanning is, as you can see here, is each one of these circles represents a scanning station. So you have to put your scanner down or walk around and really capture everything, because with the scanner, occlusions, anything that's occluding something behind the laser, the scanner cannot detect. And that's when you get holes, you know, essentially digital black holes. They have to be filled manually. And then the other side of that, LiDAR scanning a large facility is very time consuming, just the scanning itself. And then the creating the meshes usable information from that. So it's not something you would do very often if you have a large refinery or an offshore platform, for example. It's difficult to get onto an offshore platform. If you say, well, you know, we want to go out there every time a hurricane hits, we want to scan to see what's actually changed, so we can you know, keep a record of this for all different kinds of reasons. It's not really feasible. And so what we've developed in the lab is a new process that takes a simple picture, no special equipment required. And like you see here, these are two images we found online to prove out the process, and creates fully structured individual objects that you can do something with it. So again, these are just regular pictures that you can take with your cell phone or online, and then our process will create a full replica. As you can see here, that's now a digital, and we call it a digital replica versus a digital twin. So it's a replica of the built environment. You say, well, that looks like a CAD model. It does, it is not. It's not a CAD model, it's not as accurate. So because we're working with photographs, we can't get millimeter or sub-millimeter accuracy. For that, LiDAR scanning is really the choice. However, if you look at it, there's many things in a facility that, if we go back here for a second to show, if you look at this facility, do I need to scan every single inch of this tower or of these wires? Well, not really, because once I know the diameter of it, the length of it, and where it goes, I don't need to, you know, scan all of these points, for example. We're capturing way too much data. We want to capture the things that are unique and that are different. And so that's kind of behind the scenes of what we're using. But let me show you the fully interactive version of this instead of just a image. So hopefully you can all see this. So what we've created and now working on is what we realized starting to talk to companies is, well, many of these industrial companies, they don't just have one facility, they have multiple facilities. So if we take a Google Earth approach and have a platform where you can essentially select your facility and then choose where you want to go, and here we are. And so this is now using gaming technology, a game engine underneath for the visualization of this. And we can hide our character and then just interactively walk up to. And here you see the mud pump that I just showed you in the pictures. But this time, as you can see, with the textual information also applied to it. So, and as mentioned, fully structured. So on the right here, you can see the structure. Now we just gave it some arbitrary names because we're not experts in mud pumps, so we don't know what all of these things are called. And then we gave it a sample hierarchy. But each screw, each bolt are individual objects. And so once I have an individual object, well, now I can do something with it. Right? I can make it semi-transparent, so I can see what's behind it. For example, I can take the textual information off, and so it looks more like your standard CAD model. I can, highlight it. So if I select another object, the original object is always highlighted. Most importantly, now I can attach data to it, all kinds of data. So if there's any data being captured from gauges, from valves, any IoT, whatever data you may have, if that's financial data, if that's inspection data, it can all be attached here and then directly launched from the model itself, for example. Now that becomes now valuable. And again, this is not intended to replace existing software that companies may have, but to enhance everything. We can hide the object and all of its children. We can also, because our process is so fast, we can capture multiple times a year, for example, and now show change over time. So we can really see, okay, how does the object actually change as time progresses? So you get a historical record. And so it may just be, okay, in this case, it rust, or it could be dense, it could be, well, something else has been built now since the initial capture. We can attach tags to it. We can attach videos to it. There may be instruction video, how to inspect, how to repair something, how to clean it, training videos. And as I mentioned, if you have data available that you're capturing, then we can overlay that and visualize right here on the object. Now, the underlying platform is a game engine, and by its very nature is capable of multi-user interactions. So this is something now that can be served by a simple website, and multiple users all can be in this environment looking at it at the same time. The way we look at the world is from an asset-centric perspective. If you think about any company, including A&M organization, each function has their own unique software, like accounting software, HR software, engineering software, repair, training, and so on. Very rarely in any company do all of the different business functions ever look at the second most valuable thing a company has. The most valuable thing being the people, and the second most valuable being its asset. Well, imagine if everybody was starting their day looking at the assets that the company actually managed, that they actually are in charge of, versus a desktop, that's Microsoft branded. But this is your assets. This is what's valuable to your company. And from here, you're now launching whatever your function is, your training software, your manuals, your repair, and so on. and that's being updated on a regular basis. We believe that makes it extremely powerful. Now we've done a test to give you a sense of how rapid this process that we've developed is. There's 650,000 bridges, highway and train bridges in the US, and they're supposed to get inspected every 2 years. We believe through our process, because as we're doing the same type of object, the same type of installation, it exponentially gets faster because the system learns and gets more intelligent. We can capture every single bridge in the US inside of 12 months and then keep it up to date every 12 months because the process is so fast and we're only capturing really the necessary data. What do I mean by that? Look at the flow data going through the pipe. Do we really need to know every second of every day that there is 10 gallons of, name your favorite liquid, flowing through this pipe? I would say no, we don't. What we need to know is when there is not 10 gallons flowing, when there all of a sudden it's 12 or 8, when there's a discrepancy. There's no need to capture all this data and consume our resources that somebody has to wait through, because most of it is really not that useful to us. What we need to capture is the data that was edge cases, was anomalies, and so on. And so that's where we're headed with that. With that, I open up for questions.
It's great. Any questions?
Hey, I have a question.
Yes.
Yeah, this is a great talk. Thanks. This digital model is really cool. Can you talk about the reconstruction? Like what algorithm or techniques did you use to do this digital reconstruction from a single image?
Right. So we detect individual objects in the image, and so as long as we can see an object, then we can create it. So it's really based on object detection, and we absolutely need to have a picture of it. So for example, right now we're working on a project for a large energy company, for an offshore platform, and they provided us with nice, very detailed pictures. And based on those pictures, anything that's visible in the picture, we can detect it and then create the individual objects. And it works by detecting individual objects rather than just one giant mesh, because we believe having those individual objects is more useful and there's more value in that to an organization than having this giant mesh of everything.
Yeah. Oh, so you do have like a existing model, a digital model provided, for example, by the company about that machine. You already have a template.
No.
Mm-hmm.
No,
then,
we don't. No, we get a picture, a photograph.
So then you need to reconstruct the 3D model from that picture from scratch, pixel by pixel.
That is correct. Yes, that is correct.
Yeah, I was curious that it seems this is not easy. Like for example, the other side you cannot see.
Yes.
The depth information you probably don't have. So just curious, how is this done?
Right. Yes. So to help. Yes. So you're absolutely correct. Hold on, let me share with you my screen again, so you can see. Because here, for example, we did have several pictures. In fact, we had 3 pictures that allowed us to see, because we only really need, 45-degree angle pictures, to detect everything. And so that allows us to create the entire machine. However, you are correct, just like with the other processes right now, laser scanning and LiDAR, we cannot, if something is hidden from view, we can't make it up. So for example, if I hide this object and there might be something behind here, we don't know, we can't see it, we can't create it. Right, so we can't just make something up. So it has to actually be visible in the photograph for it to be created.
Okay. Okay, great. Thanks.
You're welcome.
Great. Actually, I do have a similar question. So how easy is this method then could it be combined with CID files? Consider someone gave you a CID file from some digital model that's already there. And what's the difficulty involving to combine what you are doing here with the digital model?
So we're actually, that's exactly what we're working on. Thank you, John. I don't know if you knew that. So we're working on a very large offshore platform, and the energy company supplied us with their original engineering files. So we have the CAD files that they gave us. We don't use them for the creation of the model, but what we're going to use them for is we're going to show the difference between the original engineering models and what they have today. And so they can actually see the changes that are being applied, that have happened over the years since they've created the model and what's there today. And so that's a simple overlay process. We have quite yet determined which approach, because an oil platform is a very dense environment. And so we also want to make it usable, right? So because it's not going to be helpful if you have to trying to find your way somewhere as you're walking around through the environment to find the where's a difference. So we're experimenting now. Okay, how can we most efficiently visualize at a glance the different places where there's something different, and then maybe allow you to, okay, then let me take a closer look. And again, that's where gaming technology comes in really useful, because in games, you have games where you have a 2.5D view where you see, much more of the world, and then you can go closer in and you see all the details. It's, standard thing, but we're using this to apply for an industrial purpose, to visualize exactly that. And that's a use case they have. So they want to detect what's changed from the engineering model, and then they're interested in, because it's in a place, the offshore platform where there's hurricanes regularly, they want to have an update every time a hurricane hits, is, okay, what has changed on the platform? How severe is it? How not? So they don't have to send out surveys every time to do this, but we can, the cameras that are on the platform, or the folks that are working on the platform, can take some pictures, submit them, and then we can very rapidly create the differential version for them, and so they can see those differences.
Great. I'll take this opportunity to ask one more question, since we have more than enough time for this one.
Sure.
My next question about the simulation, and you showed a very familiar simulation about fluid, going through this pipe. Now my question is, what's the technical difficulty you see for modelers like me, mostly doing simulations, to integrate our simulation results to your model, 3D model? Is there a easy and quick interface that we can do the integration?
Well, so it's really easy if you can specify the data that you produce. Because through an API, what we're doing, we're just consuming your data, and it's just a question, how would you like it visualized? So we don't actually do the simulation, but if you are doing the simulation and if you have that data, then all we're doing is we're just visualizing it on the 3D object. But we're not, and that's not our intent. We don't, because there's some really great software out there and simulations and things that capture data. We don't want to capture data or get into the simulation side. We're just consume the data and then visualize it and allow you to interact with it based on your needs. And so that would be then a discussion. Okay, what kind of data do you have? How do you want to visualize it, and how do you want to interact with it? And that would then obviously each time be a custom implementation, but we hope to get funding soon to actually develop a full platform for this, so that we have, here's a menu of options of all kinds of data inputs that you can provide, and there's already default scenarios of, here's a visualization and an interaction model for this. Because what we've seen as this becomes useful not just in the industrial space, but also in the consumer space. So you can take a picture of your kitchen, for example, and instead of having a model kitchen, it's your kitchen, and we can replace every single element in it. And so you can completely remodel your home, your actual home, your kitchen with new countertops and so on, or your bathroom. And there's so many applications for what you can do from this. So that's where we're working now. Okay, how do we create a platform to serve those different needs that may be there?
Yeah. Do you have any questions from our audience? We have someone. Okay.
Okay. How do you track operation of the machines? So we don't. We just consume the data and then display the data. So the data is basically served to us, the format, and then we just visualize it, as I mentioned to Gian. This based on advanced form of shape from stereo. And no, this is not stereo images. These are regular photographs. So your cell phone, an old cell phone, a regular DSLR camera, anything that can take a picture will suffice. That's why I said we did this with, we just downloaded a couple of pictures or 3 pictures from the internet to prove out that we have no idea who took the picture, what equipment was used for the picture, so it does not require stereo photography. In fact, the energy company we're working with, they gave us 360 pictures, really, really high detailed and panoramic pictures. And that's actually something new. We hadn't worked with panoramic pictures. We've always worked with just flat pictures. And so we're now working on, okay, it's great to have a panoramic picture, but now we have to figure out how do we actually make that work for us, because we've only worked with flat pictures so far.
Okay. We have still time for one more question. Anyone? So how about the streaming capability for the platform?
Yes. So once again, thanks to the games industry, we now have something called pixel streaming that's available to us. And so imagine Netflix, but hopefully everybody's familiar with, or something like Netflix, where you can watch a 4K or high definition video on your television. Well, the same underlying technology is now being used in the games industry called pixel streaming, that allows us what I just showed you, 3D, you just saw an image, but we can now stream that online in a web page, and you can fully interact with it at this kind of fidelity. So no longer it's really simple shapes and no textures, but at a full high res fidelity. And that technology is really, really new. And it's not yet used in the top end games, because the top end games are usually multiplayer games that are online, and many people playing together, and they're really sensitive to latency. Well, in our application, we don't have 100 people where we need to have 3 millisecond responses. So there can be a little bit more of a latency that makes it really tolerable for us, and just I think really perfect. And we're now in the middle of figuring out what underlying platform cloud infrastructure is the best to use. So we've worked with a dedicated one, but now this can be housed on Amazon Cloud or Google Cloud, and any cloud service. Essentially, you can make that work as long as they have some graphics chips that can visualize it.
Okay, that's great. Thank you.